Yeah, good evening, class. Welcome to today's lecture. Today we are going to look at what we call reading of favorite books. The objective of the day is to develop what to bring after education part for to do more action of various types of forces. And then the second one is to apply the conditions of the ability to determine some forces acting on living bodies. And the last one is to be able to draw the free body diagram of the body. Mind you, we have already talked about what the body is. And we already know what our living body is. And we already know how to resolve what forces and then how to keep them. The only new thing here is how to draw the free body diagram for the game dance. So we quickly go through the activity of the day. We look at the theoretical aspect of it. So when we meet in class, we look at how we apply these principles. We solve them like one problems, like we do the other day. So we are talking about the building of the device. Before we can even move on, we must first of all know what the building is. And for everybody, we are able to define it as what. Somebody that doesn't what define. So we already know about the buildings. And according to we have talked about it, and the resolution of forces, and taking a note of what a force in the world causes. But we can still reverse. So let's remind ourselves of what we mean by what. So now we say the body is working. Then we say that the resultant force acting on it, and then the resultant moment acting on it. All of them must be what? Zero. If that happens, then we say that the body will not rotate, and we introduce the movement condition when we are taking on it. We say that if the forces acting on the body is zero, the movement can cause the body to rotate, even though it will have no effect on all. So for the body to be in total recovery, then we shouldn't rotate. So we say that some of all the movement should be zero. Now, when it comes to the forces, there we will say that if it is in recovery, then the body will remain at rest, that is started to recovery. And if it is moving in a straight line, then it should also have what? Constant rest. So when we talk about bodies in recovery, then we want three conditions to be satisfied. That is, the body should not rotate. The body should remain at rest if it is at rest. And if it is moving, it should continue to move in a straight line. Constant rest. And that's why we have prescribed it and the meetings a lot of information. So we say that in summary, if you sum all the forces, that is if you have 2D, well, we sum forces in the X, we sum forces in the Y. And then we take the net about the words, CSs. Everything should be equal to 0. If that condition is satisfied, then I will say that the body is in what? Equilibrium. So we say that most problems in engineering mechanics involve bodies interacting with what? That is, without the body, that is finding a space without it being important to what? Another body. So whenever you have any engineering problem, expect that you might have what? So many bodies that are in contact with each other and interacting with each other to perform a particular work. So for us to analyze this problem, then we say that the body should be first of all isolated. And isolation means that if we have seven bodies, we must watch, take them one by one, and then analyze what these bodies. And then the given force system acting on the body should be what? Identified. And we have already talked about what? Force systems. You know? So you already know them. And then after isolating the body and identifying the force systems, then we can analyze to obtain what? The unknown forces. You see, as I said, and I keep saying, no matter how complicated the question is, no matter how complicated the system is, we can easily what? Break it down and make it as simple as what possible. And then from there, you can analyze and then obtain all the unknown forces. We shouldn't let how complicated the body is intimidate us. We just have to relax, analyze the system, and then we'll come out with all the unknowns. So the method that we normally use is what we call the free body diagram. And we said the free body diagram is what? A way of identifying and taking into account all relevant forces acting on the body in a given situation. So we can have maybe a whole block. We can represent that block by what? Just a single line. You see, that is what we are calling the block. We can simplify every system using what the free body diagram. So the definition of a free body diagram is that we say a free body diagram is just a simple sketch of the outline shape of what? The body. So if it is a box, then we can say that we just represent it by what? A square. You see. So we can just simply draw what? A square or a rectangle to represent what? The box. And that becomes what? Our system. And then we can easily what? Analyze. After drawing the outline shape, we say that it should be what? Isolated. So if we have 10 boxes, then we have to what? Isolate them. The first box should be isolated. The second one too should be isolated. And then the third one too should be isolated. And then we analyze them what? Separately. And then we show all the what? Surrounding forces that is being exerted on the body. So if we have a force in the water, then we can show that force. If we have a force in the earth, then we can show that force. If we have a force in the air, then we can show that force. So after showing all those forces, then we can apply our equilibrium equation. And then we come out with what? The unknown what? Forces. So how do we draw a free body diagram? We say that you must go through what? Some steps in order to draw the free body diagram. We'll quickly go through those steps. And then we'll see how best we can what? Apply those steps in simplifying what? A complicated what? Problem. So the first step is to sketch the subject body isolated from all other bodies, just as I stated in the earlier slide. If we have 3 boxes, we just have to separate the 3 boxes, you see, and then you apply your forces on it. This body may be an entire structure consisting of what? Many component parts treated as what? A unit, or it may be what? Individual parts of what? A structure. After isolating those components, then we say you show all forces acting on what? The body. And in showing all those forces, we say that you must what? You must first of all consider what? The magnitude of what? The force. You see. So if you know the magnitude of the force, then you must also consider what? The line of action of the force. And then the sense as well. Mind you, we have gone through characteristics of the force. We said that the force is characterized by what? The magnitude, the line of action, and then what? The sense. And the fourth one that we have not mentioned is the what? Point of what? Application. We didn't include it because the point of application will always be known. You see. So that one is not that what important. The magnitude, sometimes you will know it. Sometimes it might not be what given to you. The line of action, that one you must. It might be given to you. Sometimes too, it might not be what. It might not be what given to you. And then the sense, that one will say that you always have to what? Assume it. So that if the sense, if the force is negative, then you know that the sense that you assume initially was wrong. So you just point the force in the opposite direction. These forces will represent what? The effect of the what? Contact what? Forces. That means that whenever bodies are in contact, there are forces acting at the what? Point of what? Contact. So you should take note. It's very, very important. When two bodies are in contact with each other, there will be what? Forces at the point of what? Contact. Take note. And then indicate all desired what? Unknown forces with a symbol and include as much known information as possible. So if there was a force initially acting and the magnitude have been given to you, you must what? Show the magnitude. If the direction was known, you must show the what? Direction. If the sense was known, you point it in the same sense. But if it has not been given to you, then you can say that you are what? Going to what? Assume what? The sense. So we'll quickly look at some problems and then see how best we can what? We can analyze that system. So we say that we have what? A beam. That is what? Simply what? Supported. We say a simply supported beam normally supported on what? Rollers and then what? Pins. So if you look at this beam carefully, we have what? A force which has been labeled what? F. You see, the direction of the force has been given to you to be what? Theta. The point of application is at what? This point. And the sense is what? The pointing what? Downwards. Now, if you realize, if you look at the figure carefully, you realize that we have what we call support here. These are what we are calling what? The supports. Because this beam is resting on what? These what? Supports. So we say the beams are what supporting the beam is being supported by what this pin and then what the other what support. The moment you see a knife edge shape, then we say that is called what? A pin or support. The moment you see a circle, then we will say this is what? A roller what? Support. So this is a pin support. And then that is called what? A roller support. The main difference is for a pin support, we expect two reaction forces. Mind you, we said that whenever bodies are in contact with each other, there are supposed to be what? Reaction what? Forces. And if you look at this point A carefully, you realize that the beam is in contact with what? The knife edge with shape. If you look at this point carefully, you realize that this beam is in contact with this circular what? Shape. So at those 2 points A and B, we say that there should be what? Reaction what? Supports. So for a pin support, we say we have what? Two reactions. In the two reactions, we already know architecture. This is the x-axis, and that is the what? Y-axis. So we have a force in the x, and then a force in the y. So whenever you see a pin support, expect that we have what? Two reaction forces. And mind you, this force is pointing downwards. So according to Newton's third law, there should be what? Opposite force opposing what? That force. So we say it will point to what? Upwards to oppose that force what? F. And we say because at that point it has been labeled P, that force in the y we say is what? A what? 1. Now if you look at this force carefully, if I resolve it onto the x, you realize that it will point from what? Left to what? Right. And if there should be a force opposing it, then there should be another force here, which is what? A what? X. Mind you, the direction of the forces can be what? Assumed. So in case this AX is solved and then we get negative, let's say AX here. Is equal to maybe negative 10 newtons. Then we'll say that the direction we chose initially was wrong. So we have to what? Change the direction. You see. So instead of us pointing it to the left, we can say that we will what? Change the direction so that it points towards the right. And vice versa. So if this AY here is negative, then instead of pointing it upwards, we point it downwards. So those are the reaction forces at the pin support. Now if you come to the roller support, we say that you have only one reaction force, and that force is always in the Y. So we can easily point that force upwards. And because at that point we have labeled it P, you can say that this is B Y, because it is in the Y direction. And that is what has been shown here. You see. So this complicated figure here has been reduced to this simple figure. Now the weight of the beam is always acting downwards, and it is at the center. So that one too has been shown here. So instead of the B, we can say this is what? The B what? B. That is the weight of what? The B. You see. So if you have any question, you just note it down. When we meet in class, you ask me, and then I throw more light on it. So we'll move on to the next example. And we'll see how best we can what? Analyze that what? Problem as well. So with this one, we realize that we have what? A beam that is supported by what? A string. And on top of the beam, we have what? A cylinder there. And that cylinder, you realize that it's in contact with what? The wall, as well as what? The beam. And the string is in contact with what? The wall, as well as what? The beam. So that string is holding what? The beam in position. And in turn, that beam is also what? Holding the cylinder in what? Position. So first of all, we can have what? 3 free body diagrams. You see. We can have the free body diagram for the entire system. You can have free body diagram for the cylinder. The free body diagram for the what? Beam. Mind you, we said that free body diagram is first of all what? Isolate with the system. You see. So if we isolate the cylinder and then the beam from the wall, then we will say that this is what we will get. If you look at it carefully, this beam is fixed at what? The point A. And at the point A, the type of supporting system there has been labeled as what? A pin what? Support. At point C, the cylinder is in contact with what? The beam. At point D, the cylinder is in contact with the wall. And at point B, the string is what? Joined to the wall. You see. Mind you, we said that whenever bodies are in contact, they are supposed to be what? Reaction forces. Don't forget. So if we are drawing for the entire system, then we want to just what? Get rid of what? The support system. So that the cylinder, the wall, and the string will be what? Isolated from the wall. They can now be what? Placed in space for what? Analysis. So if we consider the point A, mind you, it's a pin support. And as we stated earlier, for a pin support, we have what? 2 reaction forces, one in the X and then one in the Y. You see. And that point is labeled A. So the one in the X we say is what? AX. And the one in the Y we say is what? AY. That is for the point what? A. When we come to the point B, and when we're treating triangle forces, the triangular law, we say that the force that is acting in the cable are tensile forces. And those ones are acting normal and pointing what? Upwards. So at the point B, we have what? A tensile force there. And that has been represented as shown. When we come to the point C, we say that there will be what? Another what? Force there. And then when we come to the point D, it is also in contact with the wall. There should be a force what? Here. So the force here we can say is what? F what? 1. You see. But because we have not isolated what? The cylinder from what? The beam. That F1 has not been what? Stated. But even though it has not been stated, you should know that at the point where the cylinder is in contact with the beam, there's supposed to be a force which can be labeled by any alphabet. So if this is F, then we can say this is what F1. And then don't forget, everybody has what weight, and the weight is always acting at the what center. So the weight of the cylinder is what? WC. And then the weight of the beam is what? WB. And the weights are always acting what? Downwards. So if you consider the entire system, then this is the free body diagram. Now, if you decide you want to expose this force F1, so you want to isolate this cylinder from what? The beam. Then this is what we want obtain. You see. So if we isolate the cylinder from the beam, then we can easily draw the cylinder as it has been drawn. Now, mind you, the weight of the beam is there. And then when we isolate a system, we say that all the information in that system must be represented. So the weight of the beam, which is the WC, will be represented as shown. And the force which was acting on the cylinder in the horizontal direction, or the x direction, must also be what? Represented. Now this F1 here initially was not what? Visible, because we had not isolated the cylinder from the beam. Now after isolation, because it is in contact with this body, now we can what? Bring the F1 here. So for the cylinder alone, this is what the free body diagram. Now if you pick the beam alone, then it means that we assume that the cylinder is not what? There. It has vanished. So we'll draw our beam as it is. On the beam at the point A, we had what? Two reaction forces, AX and then what? A1. Those AX and A1 have been what? Represented. Now the weight of the beam should also be represented. And then the force at the point of contact. You see, mind you, we say that whenever there's So WB also should be represented. Mind you, every information that was existing on the original body should be transferred to the free body diagram. And then the tension also must be represented as such. So basically, these are the three free body diagrams that you can obtain from this complex figure that you see. You can first of all isolate the whole system. Whereas that if you isolate the whole system, then F1 will not be seen. You see. So for us to see F1, then you must break this entire system into two. One for the cylinder and then one for the pin. So that F1 now can be shown on the various bodies. So we'll quickly look at the third one. And then we'll call it a free body diagram. So the third one we say is what? We are having two blocks with one line on the other. And the other one in turn is what? Lying on what? The floor, you see, or on the ground. So if you have such a problem, how do you analyze it? How do you come out with the free body diagram? And you will say that you must isolate the two bodies. You see. So body A, when we isolate it, you get something like this. And then if we isolate body B, you get something like that. Now after isolation, then we must come to the forces. Mind you, we said that everybody has its own weight that is acting at the center. So the weight of body A, we say is WA, and you can see it is acting at the center. Now we say when two bodies are in contact, there are contact forces there. So for body A, at this point, there should be a reaction force that we are calling RA. You see, that is for body A. Now when we isolate body B, at this point, body B is in contact with body A. So there should be a reaction force that we are calling RB. Now body B also has its own weight, and that weight will act at the center. And if you look at body B carefully, it is in contact with the ground. And because of that, there should be reaction at this point. And that reaction is what has been shown as us. Mind you, we said that the direction of all those forces can be assumed. So that if the force we get is negative, then we'll change this direction to move in the opposite direction. You see. So basically, if I isolate the two bodies, these are the free body diagrams that you would obtain. Now, after obtaining the free body diagram, how do we proceed? The other two examples we solved, after obtaining the free body diagram, we can still apply our equilibrium equation. After applying our equilibrium equation, we can find the various forces. That is, with some forces in the X, and then with some forces in the Y. So this one we can sum forces in the X. If we resolve this onto the X, AX should be equal to what? F cos theta. And you can easily solve for what? AX. Now AY minus AY plus W minus BY. And then we resolve this one to what? F what? Sin theta. We equate everything to 0. We have some equations we don't know. If we take moment about any of the points, we can easily what? Find the unknowns. This one we can do same, and then we come out with what? The unknowns. So if I consider this body, if I want to know the relationship between RC, WA, WB, RA, and RB, then all what I have to do is just what? Some forces in the X, and then some forces in the Y. But mind you, all the forces here are in the what? Y. So summation of all forces in the X will be equal to what? 0. You see. So if that's the case, then if I consider body A, if I sum forces, mind you, the WA is acting downwards, RA is pointing what? Upwards. So it means that this WA which is pointing downwards is what? Negative. And RA which is pointing upwards will be what? Positive. So RA. Everything here should be equal to what? 0. You see. Now I can say that RA here should be equal to what? W what? A. You see. Now if I consider body B, this one is for only body A. So if I consider body B, you see, I can say that this is pointing downward, so it's what? Negative. So minus RB minus what? WB plus RC. Everything here should be equal to what? 0. Now if I rearrange this one, it can also mean that WA minus what? RA should be equal to 0. If I send everything here behind what? The equal sign, this relation is equal to what? This relation. Now if I send everything here to the right hand side, then this relation will be equal to what? That relation. So there's no difference between this and that. Now we can say that according to Newton's law, to every action there is equal and opposite to what? Reaction. So if there is equal and opposite reaction, then we can say that RA here is equal to what? RB. So if RA is equal to RB, then I can say that WA here is also equal to what? R what? B. True or false? True. Because RA is equal to WA and RA is equal to RB. So WA2 is equal to what? R. So in place of RB, I can put what? WA there. So I can say that minus what? WA minus WB plus RC. Everything there should be equal to what? 0. If I take minus WA and minus WC to the other side, then I can say that RC here is equal to what? WA plus what? WB. So that is how you obtain the various what ordinals from what? A free body diagram. In this case, there was no need what? Taking moment about what? Any point. Because the weight of the block of block A and block B can easily be what? Calculated. So you can easily know that the reaction of the point to it. C. That is if this point has been labeled as what? C. So there was no need what? Taking moment. So we were talking about the fact that this is what? Yes, a pin support. This is a roller support. This is that. This is a fixed support, and so on and so forth. So look at how you represent what? All those types of what? Supports. You see. So we say if you have a flexible cable, rope, chain, or wire, this is how it and this is how it has been represented. Then this is what? The free body what? Diagram. That is why if you look at this cable system, we just represented the what? The tension in the cable by what? T. You see. So if you have any cable, then this is how you draw what? The free body what? Diagram. If you have a roller support, like I was shown, then we say that you have only what? One reaction force, and that reaction force is pointing in the positive y direction. So we take note. If that reaction is treated at an angle, then you must what? Show that angle there, the direction of what? That force, because this one is not horizontal. This angle here means that this force is acting at a particular angle. If you have a smooth surface like this is how you represent it. This one will implement it when we are dealing with what? Friction. So when we get there, we will throw more light on it. And if you have a pin support, like I said earlier, you have two forces, one in the X and then one in the what? Y, as shown. And then if you have a fixed support, this is what we call a fixed support. That one you have two forces, one in the X, one in the Y, and you also have what? A movement about what? That point. And if you have ball and socket support, then therefore we have what? Three reactions. RX, RY, and the what? RC. These ones are normally seen in there. So in summary, if I break the summation of forces and then the summation of momentum, then we say we are going to have what? 6 what quantities. You see, for the forces, if you are dealing with 3 dimension, we have fx, fy, and what x. And then meant to have what mx, my, and what mz. So we have 6 of them. You see. Now, if we have 6 of them, and then we are maybe dealing with only 2 dimensions, that is the xy plane, then we can say that if you are dealing with xy plane, then fz is what? 0. My and then mx will also be what? 0. And then the moment about the point z should be equal to what? The moment at the point what? O. So if that's the case, then we can say that all of them, if these 3 go to 0, then we'll be left with what? Summation of what? Moment in the x, because we are dealing with the xy plane, should be equal to 0. Summation of moment in the y should also be equal to 0. And then the moment at the point z should be equal to 0. So in a 2-dimensional plane, which is the xy plane, we will deal with only what? 3 what? Scalar quantities instead of the 6 here. So that is the end of the lecture. After watching the video, if you have any question, just write it down. When we meet and we are solving questions, you can ask those questions, and then we will digest it together and come out with a solution to your problems. Thank you.